I'd like to go over sort of an illustration of how this recursive function works. It's called invert binary tree. Given the root of a binary tree, we're tasked with inverting the tree. And rather than actually like a full inversion, like as if it's turned on its head or something, what it basically means is that, if you have a particular parent and then you have children, the children are then found on opposite ends. And this property would be true for, deeper and deeper subtrees. For here, it has two children, 2 and 7. The task here is that, 7 gets swapped out with the 2. And you can see in the resultant tree that, that is true. The 2 gets there, the 7 goes there. But what happens is, this tree, it just doesn't swap those values. This whole subtree gets taken with it, right? So you can imagine this whole subtree sliding across this way, and this whole subtree sliding across this way. And then, again, you perform that same operation where, the children, as we said about 4, the children are swapped. So here, we've swapped the trees, this whole subtree of 7 as its leader, so to speak, is now found on the left side, and then 2 is found on the right side. But then deeper you go, it continues, performing this pattern, which is swapping the subtrees. So 6 is now, before, if you were to take this all the way to this side, to the left, 6 would be on the left, and 7 would be on the 9 would be on the right, but then you would have to swap those as well. So then you get 9 and 6. And then the same thing could be said for this side. So you took this whole tree and you moved it this way. But in addition to moving it that way, what you've also done is you've flipped the numbers. So 1 and 3, you've done that one more level deeper. So you had 1 and 3 before, now you have 3 and 1. So you're just continually taking, this whole tree, moving it that way, this whole tree, moving it that way. Whereas in this case here is more illustrative of that fact. You had this root node, you took this whole subtree, you moved it that way, you took this whole subtree, you moved it this way. And then further on, you've continued doing that for the children subtrees. So, you had this, and then you moved it that way, just as we have here. And then you had this, this 3 here, you moved the 1 there, and then you got the resultant. And so basically the main solution to this was here, which we'll sort of explain. But if the root is null, we return null. And that's sort of the base case of the recursively defined function. And here, if we create a temp before making a swap, actually, and then we actually call recursion on the left and on the right, and we'll we call this recursive function on the left and the right, and we'll see how that how exactly that that plays out. So we can sort of craft a tree here. So suppose we had let's say 10, and this was 9, and this was, let's say 22. And for now, what we're going to do is we're going to imagine that 9 actually has 9 is pointing to null, and this pointer is also null. Even though these aren't valid members of the tree, we'll just assume that there are pointers here, or references rather, to null. I mean, there are by default, but they aren't meaningful. They aren't meaningful parts of the tree, just because if you're pointing to null, then it's useless seeing what you're pointing to. But we'll have these here just to demonstrate. So here we have the solution that we were referring to, and what we can see is that, okay, well, as we call this function for the first recursive call, and it's not really starting recursion yet, but we pass in 10, and we note that the root is in fact not null. So we actually return, the root is not null. So, this is not executed here. But what we do end up doing is we save what we introduce a temporary variable. And that temporary variable holds the left of the node in question. So the node in question is 10, the left is 9. So it actually holds the value, well, not necessarily the value, so to speak, but you can sort of think of it as it's holding this node, its memory location, its memory address. And therefore it also holds the value. But just to identify it, we'll just say it's 9, and it stores root.left. So this temp is set to root.left, and then we begin the recursive calls. So root.left will be set to the recursive call on root.right. So from this point here, we add sort of another function onto the call stack. And what happens here is, this is now, so root.left, we introduce another instance of, the function, but this time it's doing it on root.right. So it's doing it on 22. Okay. And on 22, we see that the root is not null, right? So now 22 is now our root. So the root is not null. Tree node temp is root.left. So what is 22's left value? It's null, right? So this whole idea for the temp here is actually set to null. And root.left, we do then a recursive call on, the left of 22 is now set to being the recursive call on the right. And we know that the right is null, so we actually were passing in null as a value here. And then let's see where this will take us. And what we see is that, as we pass in a value of null, this gets satisfied, because remember, null is what we were essentially passing in as a parameter, and this gets satisfied, so it actually returns null. So this returning null then shoots us back up here to root.left. And so root.left is now set to the value of null. And then we begin processing root.right. And what we see for root.right is, we create another function onto the call stack, and we do this on root.right. So, root is null. This is satisfied because, the temp we had was set to null. So this is also satisfied, and therefore, we return yet another null value. And we quickly see that root.right is also null. Okay, so, what we've done for 22 is, this may have not been clear what we've done, but what we've done for 22 is we've actually swapped this null value with this null value. So we've taken this null value and we've done sort of a swap here. And then we will do that again, upwards, right? But that's essentially what has happened. And we can't see that because they were both null, but we will see that now. So anyways, after processing what the left and the right will be for, the node that holds 22, we return the root. So the root is 22, and that root then initializes what is to be root.left. And the root.left for 10 is now set to 22. So this pointer now is actually pointing here. Okay, so now root.left, do you do invert tree on root.right? What all that did for us was it gave us 22 as a value. It reversed everything that 22 had associated with it, and all the children as well, those were also reversed, which were the null values. And then when all of those deeper levels were reversed, or not reversed, but when they were quote unquote inverted, then it was safe to invert the higher levels, which are 22 and 9. And so root.left is set to 22 now, and so that that works there. And then so now we begin processing root.write. So we do a recursive call to invert tree on temp. And remember the temp was 9. So we've produced another function here. And as you can see, the root is null. So, that will, the root is not null. So that won't execute. And then, we try doing now that we're looking at 9, we want to basically make sure that 9 and all of its children are fully inverted, right? We want to make sure that, we do this crisscross before we let 10 switch, because 10 should only switch when everything deeper is switched. So it's going to basically go through this process for 9 here. We'll actually see it do so. It will go through this process. So it's gonna, it's basically gonna say, okay, well, temp is root.left is null, right? And then root.left will store, you'll start doing it on root.write now. That is also null. We know the outcome of this. We passed in null into root.left. We get null back. So this whole thing is null. And then you start processing root.write, and then you pass in temp. Temp is also null, so you get null back. This will also be null. So what you've done is you've actually switched 2 null values. You just can't tell because they're both null. But what you'll see now is that, now that it knows that, okay, you've done this switch, now that you've successfully done this switch now to all the deeper levels, now you can do the higher level. You can let 10 do the switch. So, when it returns the root, remember the root is 9. So, root.write gets set to be 9. Okay, root.write is set to be 9. And then you return the root, which is 10, and then you're done. So root.write is set to, so this right hand here is set to 9. And that's what you've done. So what's happening here is, when you have a tree, let me change the color here. When you have a tree, 22, let's say this is 9, let's say this is 10, and this is 14, and this is like 16, and whatever, right? I mean, what you're doing is you're saying, okay, you want to do 10. Is that your motive? Okay, well, first check out 22. First check, and then check out 9. Okay, pause there. Do this guy, then do this guy. Switch their values, switch their null values, then do the switch. Then do the switch. So then it will do the switch, right? And then it will return the value upward. And then, then it will start processing, the other guy, and then it will eventually move its way down. It will do the switch on, these values. And then 22 will, now that 10 has done the switch, it will also make this guy do the switch here. And then finally we'll do the switch on this guy. And then ultimately, after all of these are, switched, these were switched before, then it's safe to go ahead and do the final switch. And then, you have, your inverted binary tree. But the idea is when you do this, when you have this pattern of crisscrossing, this would, bring you to your result. So, what you do is you sort of generalize it on the top of the tree. And if it works on the top of the tree, then you apply your recursive calls, because, if it works on something of this nature, A, B, C, then it will also work on other, it will work on deeper levels that resemble this pattern, right? Okay, these are all just the first case sort of repeated, right? I mean, this is also the first case. This is also the first case. This here is also the first case. So these are all just the first case. So if it works on the first case, I mean, what we do about the first case, we said, okay, well, if it's, you wanted to think backwards a bit, if it's null, then you just return null, and what we wanted to do is we're like, okay, fine, we're looking at a node. Before making a switch like this, we want to store, before making a switch like this, We want to store one of the nodes in a temporary value. So we did that. And then root dot left will, you do the recursive call on the right subtree, you do the recursive call on the left, but instead of doing left, you're actually doing it on temp, and then you return the root. And that's essentially how we got that there.